Alright, today we're going to have a quick video talking about the geometric and algebraic multiplicities of eigenvalues and basically how we can tell if any given matrix easily just by looking at all its eigenvalues and then the eigenvalues geometric and algebraic multiplicity, how we can tell if the matrix is diagonalizable. So if there exists, a form of the matrix where we choose a basis such that the matrix, can be written in only diagonal terms, or if it's not diagonalizable. So that's a hard word to say, diagonalizable. But anyways, how do we do it? It actually, it's not very complicated, but there are a few things we have to watch out for. So first of all, the defining property of an eigenvector, AV equals lambda V. That means, applying a linear transformation, applying a matrix to a vector has the same effect as only scaling a vector by a constant lambda. So lambda is just a scalar. Again, so if you have a vector, applying a to it, the only thing that happens is it stretches. If lambda is 2, that means it's going to become 2 times longer. If lambda is 1/2, it's going to become 1/2 its length. It's going to stay on its span. It will not be knocked off its span. That is a defining property of an eigenvalue. Of an eigenvector. And, this amount here, by how much it gets scaled, that's the eigenvalue. And with this definition, we can actually get so much information out of it. So let's start, rearranging this a little bit. Because, just with this, let's say we have a random matrix, 3, 4, 5, 6, 7, 9, 2, 2, 5. How do we find the matrix's eigenvalues and eigenvectors? Well, first of all, let's subtract this. Let's subtract it from both sides such that we're gonna get AV minus lambda V equals 0. And then what we can do is, again, these are vector quantities. This is a scalar. This is a matrix. If we factor out V, we get the expression A minus I lambda V equals 0. Again, we have to multiply this scalar by the identity matrix and with all ones on the diagonal I, which is the same size as A, because we can't subtract a scalar from a matrix. If we want to do it, we gotta turn the scalar into a matrix. So it's just gonna be a matrix with lambda on the diagonals. So once we do that, we see, and all this equals 0. Once we do that, we see that actually we get a new matrix over here, and this new matrix sends this eigenvector to 0. And what's the defining property of any matrix? So, any matrix obviously sends the 0 vector to 0. But if it sends any other vector which is not equal to the 0 vector to 0, that means the determinant of this matrix has to be 0. And because, we said that, we said this is true, so we know that there exists a non-zero vector such that this holds. That means this has to hold. And that means this vector sends this vector to 0, which means the determinant of A minus I lambda has to equal to 0. This fact helps us find all the eigenvalues. So all the eigenvalues, and I think that's actually really clean. Just this simple rearrangement of this equation, we just got an expression on how to find. We just found the method on how to find every single eigenvalue of the matrix. So again, we have a matrix. I'll do two examples later with a diagonal matrix and a non-diagonal matrix. But basically, we get a matrix. We just subtract lambda from all the sides. Then we find its determinant, and what we're gonna get at the end is a polynomial equation, which is called the characteristic polynomial. So we're going to get a polynomial in lambda, and the roots of the polynomial will exactly be the eigenvalues of the matrix. And sometimes the roots can be repeating, and sometimes they don't have to be. We're going to talk about this in a second. But basically, that's how we find all the eigenvalues. And how do we actually find the eigenvectors? How do we find the eigenvectors associated with each eigenvalue? Again, I'll do examples on this very soon. Well, we know basically that A minus I lambda V equals 0, and we already found, let's say we found the eigenvalues. Let's say the eigenvalues of a 3x3 matrix are lambda equals 2, which appears twice, so it has algebraic multiplicity 2, and another eigenvalue, let's say lambda equals 3. Well, then we know that the roots of the characteristic polynomial will be like 2 minus lambda squared and 3 minus lambda. This is how the characteristic polynomial is gonna look like. But you're gonna see this very soon. But basically, that means for the eigenvalue of 2, we plug 2 in here and we change our matrix. We subtract 2 from the diagonals, and then we want to find what vectors this matrix sends to 0. So we have our little matrix A minus I, let's say lambda 1 for our first eigenvalue, which is going to be 2. So we have this matrix. If our matrix was just a simple 1, 2, 3, 4, then this A minus I lambda, if lambda is 2, we just subtract 2 from the diagonals. So it'd be minus 1, 2, 3, and 2. So this is our change matrix, and then we know that this matrix, we want to find what vectors it sends to 0. Let's say it's a 3x3 matrix, so x, y, z, and we want to find all the vectors that this matrix sends to 0. So we got to solve this linear, system of equations, and by that we basically find the kernel with this we're going to find the kernel of A minus I lambda, which are all the vectors which this matrix sends to 0. And again, since the determinant is 0, we know it must send, at least one line of vectors to 0. It must send at least one dimension of vectors to 0, but we don't know if it sends multiple dimensions to 0. That's the whole trick. We can have a whole, we can have the whole vector space. Let's say it's a 3 by 3 matrix. We know since the determinant is 0, it sends like one line of vectors to 0, but it could send the whole plane of vectors to 0. We don't know that. If the algebraic multiplicity of our eigenvalue is more than 1, so let's say if it's a repeating root, if it happens twice, that means it could send, also two-dimensional vectors to 0. We're going to see that soon. But basically, we usually reduce this to row echelon form, and then we just solve this system of equations, and we're going to get values for x, y, z, and then we're basically going to find the basis for this matrix. We're going to find the basis for this kernel space. This is going to make way more sense when I show the example, but basically once we find, we can maybe see like, x has to equal 2z, and, y has to equal 0, and then we basically find the basis with these constraints, and these basis vectors are going to be exactly the eigenvectors. So the vectors in the kernel of this, which we get from this equation, are going to be exactly the eigenvectors of the specific eigenvalue. And we do that for each eigenvalue, and then we're done. Basically, now what's going to happen here, the amount of vectors in the kernel, so the amount of vectors in the kernel of this this specific matrix, that's called, this is going to be, so the dimension, actually, if I say correctly, the dimension of the kernel of A minus I lambda, that is going to be the geometric multiplicity. Geometric multiplicity of the eigenvalue lambda. So the geometric multiplicity is the number of linearly independent eigenvectors, for a specific eigenvalue, and the algebraic multiplicity will just be, the amount of times that this lambda appears in the characteristic polynomial. So again, if we get a characteristic polynomial like 2 minus lambda squared and 3 minus lambda equals 0, we can get this for a 3 by 3 matrix. The geometric multiplicity of this eigenvalue, which equals to 3, is 1, and the geometric multiplicity of this eigenvalue is 2, because again, lambda solves the equation twice. It's a repeated root. And basically, the nice thing we have is a matrix is diagonalizable, so is diag, I'll just shorten it, if the algebraic multiplicity, which I just say akara lambda, I got used to this, I don't know why, I think we did it in uni, if the algebraic multiplicity of every eigenvalue equals the geometric multiplicity, which I call jkm lambda, well, if this is true for every single eigenvalue, then the matrix will be diagonalizable. So for this eigenvalue, if we get two eigenvectors from this expression, and for this one, if we get one eigenvector from this expression, we know the matrix will be diagonalizable. And another thing we know, again, I'm not going to really go into detail why this is true. I'll do this in a different video, but just what we know is if the algebraic multiplicity of an eigenvalue equals 1, that means the geometric multiplicity also has to equal 1. Which means if we, if we have a 3 by 3 matrix, and if we get 3 distinct eigenvalues, that means, they each have an algebraic multiplicity of 1, because also, another fact is the algebraic multiplicity has to add up to n. So if we have a 3 by 3 matrix and we get 3 distinct eigenvalues, like lambda equals 1, lambda equals 5, lambda equals -2, then we know they all have to have an algebraic multiplicity of 1, because it has to add up to 3, and then we know that the geometric multiplicity, if this is 1, geometric also has to be 1, so we know it's diagonalizable already. But there's a small problem, this is the most kind of complicated part of this. If the geometric multiplicity of an eigenvalue is greater than 1, the geometric multiplicity could equal the algebraic multiplicity. It can't be greater than it can't be, but it can also be less than the algebraic multiplicity. So the geometric multiplicity of an eigenvalue can always be less than or equal to the algebraic. And that's where the problem arises. If we have a repeating root, let's say 2 minus lambda squared, we can have a problem because it can have two linearly independent eigenvectors, the kernel of this eigenspace, or it can only have one. And as soon as the algebraic multiplicity is smaller, as soon as the geometric multiplicity is smaller than the algebraic one, then the matrix is no longer diagonalizable, and that's the whole trap. And then it's over. Then it doesn't work. Which is why we have to be so careful sometimes. And I think now it's actually time for me to start with examples. So because the examples are where it all makes sense. So first of all, let's have a 3 by 3 matrix, 2 3 3 0 2 0. I'll just keep it as simple as possible, 0 3 5. And now, what have we talked about? Well, first of all, how do we find all the eigenvalues of this matrix? Well, we want to find the determinant of A minus I lambda. I mean, we know that the determinant of this has to be 0. We talked about this before. So, a minus I lambda, that means we just transform this matrix into this matrix where we subtract lambda from the diagonal. So 2 minus lambda, 3, 3, 0, 2, 2 minus lambda, 0, 0, 3, and 5 minus lambda. That will be, our new matrix, and we want to find the determinant of it. And usually, when you want to find the determinant of a matrix, you just put it in like, lines like this. And so this is basically the determinant, and we want this to equal 0. So, again, I'm guessing you already know how to do this. This is a 3 by 3 matrix, so, we're going to expand along this line to find the determinant. Everyone has their own way of finding the determinant. This is the easiest, I think. So 2 minus lambda, and then I basically have to find the determinant of this. I forgot what this is called, but it's the most classic rule. So we're going to have this times 2 minus lambda, 5 minus lambda minus 3 times 0, which is just 0. So we get this over here, and this has to equal 0. So, oh my goodness, what is our characteristic polynomial? It's 2 minus lambda squared, 5 minus lambda equals 0. So this is our characteristic polynomial, and we see instantly that we have, our first eigenvalue will have a value of 2, and we're going to see that it's algebraic multiplicity. So of this first eigenvalue equals 2, because it's a repeating root. And our second eigenvalue, lambda 2, is going to equal to 5, and its algebraic multiplicity equals 1. So we also know its geometric multiplicity equals 1. So for this, we don't have to worry about it. This is chill. But for this one, we have a problem because this has an algebraic multiplicity of 2. So if we want to say whether the matrix is diagonalizable or not, we first have to check if the geometric multiplicity, so if the geometric multiplicity of this eigenvalue also equals 2. Does it also equal 2? Well, we can't check. It could equal 1. It can equal more than 2. It can't be 0, but it could be equal to 1. So we have to check this out before we can tell if the matrix is diagonalizable or not. So how do we do this? Well, again, we find the dimension of the kernel of this space. So basically, we have, we take this matrix. So, we have to find the dimension of the kernel of a minus I lambda 1. So what vectors, this matrix with eigenvalue 2 sends to 0. So again, we have our little matrix, this is our underlying matrix, and we subtract from it 2 from the diagonals because we have a minus I lambda 1 is 2. So after subtracting 2 from the diagonal, we're left with 0, 3, 3, 0, 0, 0. Here the 2 disappears, and here we have 0, 3, 3 because here it was 5. So we just subtract 2 from all the diagonals. This is what we get. And now again, we want to see what vectors, so I'll just label it ABC, what vectors this matrix sends to 0. And we can always simplify this by, by simplifying this matrix using row operations. Again, I'm hoping you're familiar with this, but we can subtract, this term from this term so that all these become zeros. And so, we get 0, 3, 3, 0, 0, 0, 0, 0, 0. And we can divide, this top term by 1, so by 3, so we get 0, 1, 1. 0, 0, 0, 0, 0, 0. We simplify this matrix using elementary operations. A, B, C equals 0, 0, 0. This is our system of equations. This is how we find the kernel. So what do we get? If we just if we multiply these vectors together, here we all get 0, so it doesn't matter. But for the top one, we get B plus C equals 0. That's our only constraint, which means B equals negative C. So and A can be anything. A can be any number in the field. So what do we get is that to express these constraints, we see that we actually need 2 vectors because our vector is going to look like B equals negative C. A can be anything. Let's say B equals negative C, and then we have C over here. This is our vector. So to actually express this, we actually need 2 vectors. So we can have A and then 1, 0, 0 plus C and then another vector 0, negative 1, 1. This is how we actually to express this, we need 2 terms. A can be something and C can be something. So we actually have 2 separate vectors, which to express this set of equations. So basically, we can say that our basis for this kernel space can be the basis vector 1, 0, 0, and the other basis vector is 0, negative 1, 1, and then we can have any multiple of these 2 vectors, and these equations will still hold. That's what we just showed. So that we have 2 basis vectors. These are the these are the specific eigenvectors of this eigenvalue lambda. So both of these eigenvectors have eigenvalue lambda. If we apply the matrix A, they're just going to get stretched by 2. So if we apply A to this one, it's going to become 2, 0, 0. This one's going to become 0, negative 2, 2. And we see that we have 2 of them, so that the dimension equals 2, which means the geometric multiplicity of our first eigenvalue, with eigenvalue 2 is going to be 2 because it's the number of linearly independent eigenvectors. Bang! And we know that the matrix is diagonalizable. Whoo! And now, so this is easy. This is great. And now we have another example. We have a very similar matrix. Now let's say in your test you get this matrix over here: 2, 4, 3, 0, 2, 0, 0, 3, 5. Now, I mean, there's also kind of simple ways to see this won't work just because, well, I don't really get into the detail of that, but basically, what about this matrix? Is it diagonalizable? Well, let's see. First of all, you already know the drill. Let's find the eigenvalues of this matrix. 2 minus lambda, 4, 3, 0. 2 minus lambda, 0, 0, 3, 5 minus lambda. We subtract lambda from all sides. Then we find the determinant of this matrix. Again, we're gonna expand along this line because it has a bunch of zeros. Our characteristic polynomial would be 2 minus lambda times the determinant of this over here, which is gonna be, again, 2 minus lambda, 5 minus lambda, and that equals 0. Oh my goodness, we have the exact same characteristic polynomial. 2 minus lambda squared, 5 minus lambda. So with this, you can already see the characteristic polynomial is not unique. It doesn't actually depend on the matrix. You can have two different matrices. Here, there's a 4 instead of a 3, but the characteristic polynomial is still the same. So we have an eigenvalue lambda 1 equals 2 with algebraic multiplicity of lambda 1 equals 2 because it's a repeated root. And then we have lambda 2, which equals 5. And again, it's algebraic multiplicity equals 1. So here geometric also equals 1, so we're chilling. For this one, again, we don't know. We have to check if the geometric multiplicity also equals 2, and then we can say, that the matrix is diagonalizable or not. And also forget to mention, once we check that the matrix is diagonalizable, then, we can write it in diagonal form, so just with all its eigenvalues, 2 to 5, and then, the basis vectors are the eigenvectors. But I'm hoping you already know that. This is just a quick recap of geometric and algebraic multiplicity. So basically, how are we going to find the algebraic multiplicity of these how are we going to find the geometric multiplicity of this? Well, we already went over it. Again, we have to change our matrix. We have to subtract 2 from all sides. So, we subtract 2 from here. We basically, use this equation, plug in lambda equals 2. We get 0, 4, 3, 0, 0, 0, 0, 3, and then 5 minus 2 equals 3, if I'm not mistaken. So, again, and then this ABC equals 0, 0, 0. Let's find the dimension of the kernel of this space. First of all, it's always great to simplify the matrix. We don't have to, but we can simplify it. We can subtract this row from the top row, so we get 0, 1, 0, 0, 0, 0, 0, 3, 3, and then we can divide this bottom row by 3. So what we're gonna get is 0, 1, 0, 0, 0, 0, 0, 1, 1. This simplifies it a lot, and again, the answer does not change. If we use elementary row operations on this, we're still gonna get the same dimension of the kernel. So we get this has to equal 0, 0, 0. So what equations are we left with? Well, multiplying this side by this side, we get, b equals 0. That's our first constraint. And then we also get, multiplying this by the bottom side, basic vector matrix multiplication, that b plus c has to equal, this over here, which is what? Which is 0. Which means if b is 0, c also has to equal to 0. And a, there's no constraint on a can be anything. So now these are our set of constraints. And how do we, craft a vector? How do we craft a basis which, takes all these constraints into account? Well, a can be anything, b is 0, c is 0. So again, if we just take a out, we only need to take, a out, and we get this vector. So this is the basis of our kernel. It's only one vector, and then a is just, so this is an eigenvector, and again, also any multiple of the eigenvector, this is 1, 0, 0. Any multiple of this eigenvector, is also on the span of the eigenvector, so it's also an eigenvector. But we can see that the basis is only a single vector. It's a one-dimensional basis, 1D basis. So the dimension of the kernel is 1. We have one linearly independent eigenvector, which means the geometric multiplicity of our eigenvalue equals 1. And it doesn't equal 2. Oh my goodness. Before it equaled 2, for this matrix, it doesn't equal 2, which means this matrix is not diagonalizable. There also exists another eigenvector for this eigenvalue, but there's only 1 for this one, because again, algebraic multiplicity is 1. For this one, there could be 2, but there wasn't. There was only 1. So we only have 2 eigenvectors. We do not have 3 eigenvectors. And it's a 3 by 3 matrix, so we need 3 eigenvectors for it to be diagonalizable. So it's not diagonalizable. Bang, it's over. That's it. That's the end of the video. The real question is, why can the geometric multiplicity be less than the algebraic multiplicity? That's like a big question mark. What allows it to be less? And where does that third eigenvector go? Why is it not there? I'm gonna make another video on this right now because it's actually really cool. It goes a bit deeper into the actual, into the intuition of why, the geometric multiplicity can never be more than the algebraic one, and what the algebraic multiplicity actually tells us. Because the geometric multiplicity tells us, the number of linearly independent eigenvectors, Okay, that's cool. But what does the algebraic multiplicity tells us? You know, it's the repeated roots of the, you know, a characteristic polynomial. But what does that mean? What does it actually tell us geometrically? And I'll answer that soon in the next video. So yeah, that is it. Thank you for watching. Bang. I'm out. See you later.